Swayam Prabha. Digital India. Educated India.
Dear students, I welcome you to this second lecture on crystallography. So, we are beginning crystallography today, and we will first start with the concept of symmetry in crystals here. So, let us have a look at this particular diagram here. So, what you see here, so there are different geometries you can identify here. So, these are the brachiopod shells here. So, these are starfishes here, and these are some gastropods if you can see here. You see there is some symmetry you can find out. So, for example, if you see this particular shell here and these four shells, these are related to each other. If we think at this point there is a vertical axis which is rotating this shell to 90 degrees, so that it comes here, and if it also rotated 90 degree, this will come here, and another 90 degree this shell comes here, and another 90 degree this shell comes here. So, you see there is a periodicity of the occurrence of this particular objects here, in this case pellucidal shells, or these are bivalve shells here, if you can see here, and they are related to each other by symmetry operation. And you will find out that this 90 degree operation rotation that we are seeing here with respect to a vertical axis, we will learn that this is we will be calling this kind of rotation a rotational axis as a fourfold axis of rotation. I showed you here this angle of rotation that is involved here. So, the angle between these two lines here is 90 degree. So, you rotate each shell here 90 degree, and it will develop this periodicity here. This is also applicable all these other features here. And once you have this, so you can translate along a particular direction. So, the entire pattern that is developed here. Now, the important thing here is that here we need to know three important definitions here. The first is we need to know what is motif. Motif is the fundamental part of a symmetry design that when repeated creates the whole pattern here. So, in that particular diagram, the motif was that shell. And what is the operation? This is some act that reproduces the motif to create the pattern. And what is an element? Essentially symmetry element, an operation located at a particular point in space. In that particular example, the symmetry element was a rotation axis. In that case, it was a fourfold axis of rotation, which I will introduce shortly here. So, we have learned that there are three basic definitions we need to know: the definition of motif, the definition of symmetry operation, and the definition of symmetry element here. Now, let us introduce this one type of symmetry element, which are rotation. So, let us we start with this motif here, which is now shown as 6 here. Now, if you rotate, so if you rotate say 180 degree, so 6 now comes here at 9. So, you see 6 comes to 9 by 180 degree rotation, and another 180 degree rotation, this comes to the position and coincides its original position here. So, what happens here, that if we rotate 360 divided by 2, that is 180 degree, that we call it as repeat angle here, and the axis along which this rotation has taken place, we call it as a rotation axis, and the foldedness of this rotation axis is we call it as twofold axis of rotation. And if we divide 360 divided by the foldedness, that is 2, the repeat angle comes as 180 degree here. And for each rotation axis, there is a symbol that is given here, and I will be using this symbol of compressed ellipse. So, this is the symbol of twofold axis of rotation, and we will be calling this as dyad. Now, let us show you another specific example of twofold axis of rotation. So, this is an S. So, you see that it is now rotated. So, this is 90 degree rotation, and then so this is 180 degree rotation. So, it comes back to its origin. So, S has a symmetry of its own. So, it is essentially the original motif itself is a symmetry operation of two-fold axial rotation that is lying right here. Now, let us consider another type of rotation axis called three-fold axis of rotation here. And what will be the repeat angle here? The repeat angle will be, as I told you, 360 divided by the foldedness. Here the foldedness is 3. So, repeat angle will be 120 degrees. So, what will happen here? So, if it is my starting position here and this is the axis is vertical. So, that in this plane of drawing, so this is projected as a point here at the center, and this is a triangle is shown as a symbol of three-fold axial rotation. So, what happens here? You rotate 120 degree. So, 6 comes here, another 120 degree it comes here, and another 120 degree this comes here. So, with a starting motif position 6, it produces two additional motif, one here and the other here. So, this is the example of a symmetry operation of three-fold axis of rotation here. Now, I show you another variety of fundamental symmetry operation called inversion. So, what is an inversion here? So, inversion, if this is the center and if this is 6 here, inversion means that if you join with each point on 6 and you join with the center and project in the opposite direction to the same distance here, and it produces now a 9 here. So, this is called inversion operation here. One important thing that we will be noting that the inversion produces a 3-dimensional symmetry here. So, I will come to this part slightly later in some more details. The third type of symmetry operation is shown here. If this is a mirror plane here, so with respect to the mirror, 6 is reflected and this image is produced here. So, reflection operation is another type of fundamental symmetry operation here, and the symbol of presence of mirror or reflection plane is a bold line, or in some cases a bold curved line is given here. Now, I give you in this particular talk I will be using certain methodology or certain geometry that I will be using for all the different types of symmetry operations here. So, what I will do here is that I will use a circle as the plane of drawing, and I will use an open symbol or a closed symbol as a motif. So, in this particular case what I am doing here is that in this particular case this open circle represents a motif which lies at a height h above the plane of drawing. If you have the minimum symmetry operation, that is if you have a one-fold axis symmetry, the repeat angle is 360 by 1 360. So, it does not produce any additional motif here. In case of two-fold axis symmetry, which we call it as dyad, this is a symbol of a dyad which is vertical. So, it is rotated 180 degree, it comes here and it rotated another 180 degree and it coincides with the original position here. So, this particular motif lies at a height h above the plane of drawing. This is also lying at the height h above the plane of drawing. So, these two motifs are two-dimensional, they are lying at the same plane. Now, this is an example of a three-fold axis of rotation symmetry, and I will call it as this triangle. It gives you symbol of a presence of a triad. This is vertical axis, and this is 120 degree rotation here, another 120 degree comes here, another 120 degree, it coincides with the original position here. So, the presence of a three-fold axis of rotation with a starting motif, it generates two additional motif here. Now, you have four-fold axis of rotation, we call it as tetrad, and this is the symbol of a tetrad, a square that is shown here, and this is the starting motif here. So, the repeat angle is 360 divided by 4, that is 90 degree. So, the repeat angle after 90 degree, this comes here, another 90 degree it comes here, this open circle is rotated another 90 degree and after 90 degree here. So, what happens here with this starting motif, this operation of fourfold axial rotation has produced 3 additional motifs here. So, the total motifs is now 4. Now, you have a 6-fold axial rotation, which is a vertical orientation here. What happens here is that this symbol is shown is a hexagon. So, it is called as hexad. So, this kind of axial rotation, which is a 6-fold axial rotation with a repeat angle is 360 by 6, that is 60 degree. So, you see that is a 60 degree rotation. So, this comes here, another 60, it 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 coincides with the original motif here. So, what you are seeing here is that 6-fold axial rotation produces with a starting motif here is an open circle, 5 additional motifs here. So, total motif is, say for example, in this case is 6. Now, you have this particular bold line is shown as a vertical mirror plane. So, this is a vertical mirror plane. So, this is a motif which lies at a height h above the plane of drawing. After reflection, this is produced here and at the opposite same distance, but opposite to this, and it will lie in the same plane here. So, this is an example of reflection here. And now, you have the inversion here. So, you see that this symbol tells you that this is it is a motif which lies at a height h above the plane of drawing. So, in case of inversion, what will it tell? Inversion center is here. So, I will join this motif which is lying at a height h above the plane of drawing with the center, and I will now project it in the opposite direction. That means, it is going below the plane of drawing and it comes here at a distance which is the same distance. That means, it will also be lying at the same depth, at the same value h, but now it will be at a height h below the plane of drawing. And to show that this is the position, this is the projected position of that motif at lying at a height h below the plane of drawing, I have used a closed symbol here. So, in this particular talk, I will be using 2 types of symbols here. One is open symbol and another is closed symbol. Closed symbol will be for a motif which lies at a height h below the plane of drawing, and the one open symbol at a height h above the plane of drawing. Okay. So, what is important here is that we now have 6 unique 2-dimensional symmetry operations that we have studied here. 1 dyad, triad, tetrad, hexad and mirror, where all the motifs lie in the same plane above the plane of drawing. So, this produces 2-dimensional motifs here, and that is why these are 2D symmetry operations. Rotations are also called congruent operations because reproductions are identical, whereas inversion and reflection, the reproductions are opposite handed. Right hand becomes left hand and left hand becomes right hand here. Okay. Now, one of the important aspects here is that in crystallography, there are only 1-fold, 2-fold, 3-fold, 4-fold and 6-fold axial rotation is possible. 5-fold, 7-fold, 8-fold and 9-fold axial rotation or any other rotation is not possible. And I will show you the trigonometric proof or trigonometric support for this kind of why this rotations axis are not possible here. So, what we will do here is that let us consider that you have a row and this is one motif here, and along this direction this motif is translated along one repeat length here. Let us consider that is A. So, one is translated along this direction. So, after translation for a distance of A unit, this comes to position 2 and then it is translated along this direction, and then the final position is the mth position here, where it comes here, and the preceding position is m minus 1th position here. So, this is a row where it contains this kind of motifs here. Now, let us consider at position 2 there is an n-fold axis of rotation. So, what will happen? The repeat angle, let us consider this is theta, and theta is for your definition 360 divided by n. So, what happens? So, in that situation 1 after rotation with respect to an n-fold axis of rotation positioned at 2, that is a vertical orientation. So, 1 is repeated here as 1 dash and m is repeated here as m dash here, and it produces. So, one you produces 1 dash here. You can also translate along the same repeat distance a, and you finally coincide with m dash here. So, what happens here? Let us the distance between 1 dash and m dash, these two motifs here. Let us this is the value is t, and let us consider that value is equal to a multiple of p, where p is an integral multiple. So, if you have the value, an integral value, and you multiply with a, this will be the distance t. Now, we can in row b, we have this distance here. We can make an equivalence here as well. So, if we can draw a perpendicular on this, and if we can draw a perpendicular on this, so I can have this distance I can measure, and I can also measure this distance here, and these two distances if I join with the distance between 2th position and m minus 1th position, then that distance will be equal to t. So, what we have here? T is equal to then. So, what will be the distance between 2th position and m minus 1th position? So, this will be essentially the distance between 1 and mth position is m minus 1 into a, and then if we will the distance between 2th position and m minus 1th position, I will subtract a and a from both end. So, we will have m minus 1 a minus a minus a, that is m minus 3 a. That will be the distance between 2th position and m minus 1th position. And then I will add this distance here, this particular distance from here, if I draw a perpendicular here. So, this distance is a cos theta. So, a cos theta here, a cos theta here. So, we have 2 a cos theta here. So, what you have now here is that this t is equal to p a is equal to now becomes m minus 3 into a plus 2 a cos theta. So, what we can rearrange this particular one here, we can have cos theta is equal to 3 plus p minus 1, and the entire part is under this third bracket and divided by 2, where theta is equal to 360 divided by n. And you now know that both p and m are integers. So, they will not have values which will be fraction. So, we will see that unique solutions are there for p minus m values of minus 1 to minus 5. Let us see what happens if you have a value of minus 1. So, when p minus m is equal to minus 1, so this becomes cos theta is equal to 3 minus 1 divided by 2. So, 2 by 2, that is 1, and cos theta is equal to 1 means cos 0 is equal to 1. So, cos 360 minus 0. So, essentially this is 360. So, theta is equal to 360, and the foldedness of the axis will be 360 by 360 is equal to 1. When you have p minus m value is equal to minus 2. So, what you have here in that situation? So, if you put minus 2 here, so 3 minus 2, that is 1 by 2. So, this becomes half. So, cos 60 is equal to half. So, then theta is equal to 60 degree, and 360 by 60, n becomes 6, that means this becomes 6-fold axis rotation here. And if you have p minus m is equal to minus 3 here. So, what it becomes? 3 minus 3 is equal to 0. So, cos theta is equal to 0. We know that cos 90 is equal to 0. So, 360 divided by 90. So, this is n is equal to 4, that is 4-fold axis rotation here. So, when we have p minus m is equal to minus 4,